Awesome. More abstract garbage collection out of Utah.
That's right. Yeah. I mean, you thought we had plumbed the depths, but
No.
there are more. Okay, so this is the talk about abstract interpretation. If I am not clear about anything, please ask questions during the talk. I prefer that. So because this is Scheme, we're going to talk about some interpreters in Scheme, and we're going to talk about two approaches to abstract interpretation. And just to kind of gauge the room, who here is familiar with abstract machines? SmallStep abstract machines. Abstracting abstract machines. Okay, all right. Okay, so we're going to talk about that first, abstracting abstract machines, but we're going to start with just SmallStep abstract machines. So what we're going to do is define a machine to execute our programs, and we are going to consider the states that our machine enters as it executes the program, and there are two different types of states, an evaluation state and an apply state. So the evaluation state has these components. It's got this expression component, which is analogous to your program counter, an environment component, which is like your stack frame, which contains your local variables, a store component, which models the heap. This is analogous to the heap. The continuation component, which is like the rest of your stack, and it contains your control linkage information. And then a timestamp, which I'll mention along the way, but that's mostly used for allocating stuff in the heap. And then when you have an apply state, that means you've evaluated an expression and you have a value, and now you need to apply your continuation to it to continue. So we are going to consider, and then to define the actual evaluator, you're going to define a function that takes in a state and returns a list of states. And it is shaped kind of like this. You're just going to pattern match on the state, and then I have these specialized functions that we won't go into, but they're straightforward. So we're going to consider this program, and during the course of this talk, we are going to interpret this like 6 different times in 6 different ways. So this program, it binds the identity function, and then it calls it on 42, binding the result to y, calls it on 35, binding the result to z, and returns z. This is Scheme, so I assume we can stop there. So we're going to go through the execution of this in a SmallStep abstract machine. So this is not an analysis. This is actually just an execution. And what we're looking at now is a representation of the initial state of that machine. So the code highlighted in blue is the control component. That's the expression we're evaluating. When there's code not highlighted in blue, that's the continuation. We've got the store on the right, and the environment will be represented by arrows from variables to the things that they point to in the store. And the time here, we will not see the time at all. In this setting, it's just used to make sure that when we allocate something in the heap, we always get a fresh cell. Okay, so the first step is to sort of look in the expression and find the thing that we're going to evaluate. So now we're evaluating this lambda term, and the continuation is this let ID and its body. We enter an apply state, and when we apply this value to the continuation, it's going to allocate something in the store. So now these references to ID point to something in the store, a closure in the store. And we continue in this way. First, we identify an expression. Now, when we evaluate this call, it will be replaced by the call's body, and 42 will be bound to the parameter of the ID function. And then we'll continue to evaluate this variable reference, and then we apply. And we'll just continue in this way. And we end up applying 35 to the empty continuation, so we're done. Okay, so I'm going to run through this again very quickly and just point out one thing, which is as we evaluate, so here we have the identity function, which is reachable from the current environment. But as we evaluate, there will become, we will come to things in the store that are no longer reachable, like this 42. And by the end of evaluation, nothing will be reachable because we're just returning a number. And so all of this is garbage. So we're going to enhance our interpreter here with a garbage collector. And that's really easy. We're going to go from this shape on the left to the shape on the right. All we're going to do is map the resultant states with the function GC. And GC works kind of how you would expect. We need to get a root set from the continuation and the current environment. We calculate the reachable addresses of that root set, and then we restrict our store to those addresses. OK, so if we evaluate this function again, or this program again, with garbage collection, then whenever we're performing garbage collection at every step. So once we're at this point, where this 42 is no longer reachable, garbage collection will collect it. And we go in this way. OK, so I think that's pretty straightforward. Now, the important thing, there's an important distinction that I'm going to make later, but it's important to note that garbage collection obviously does not change the result of the program. It would be incorrect if it did so. So now let's talk about abstracting this abstract machine. And we're going to go through basically 4 steps. The first step is to store, allocate our continuations. Then we're going to finitize the address space. And when we finitize the address space, that means we are no longer able to get a fresh heap cell whenever we want. So when we allocate and are not allowed a fresh heap cell, we're going to store multiple values in the same heap cell. The third step is to consider every alternative. And so that means if we ever reference a heap cell with multiple values, we need to consider both and consider the execution that would arise when either alternative was picked. And then the fourth is to mark where you've been. Once we finitize the address space, there are a finite number of machine states that we'll encounter. And if we don't explore a machine state we've seen before, then we have a terminating algorithm and we have an analysis. OK, so let's look at this. So the states, they have the same shape. The difference here is that addresses or continuations have turned into addresses, and they point to the heap. And then also, at least for this example, times are going to be a singleton set. So once again, we won't see them explicitly. OK. So now we've got this expression on the left, and it is pointing to its continuation, which is the empty continuation in the store. And when we sort of go into the expression and identify a sub-expression to evaluate, we build on that continuation. And so we're pointing to our continuation frame, and it is pointing to its next continuation frame. And this continues. OK, so the store we can see is quickly getting overloaded by continuations. I think this step is going to be the interesting one. Not quite. OK. OK, so that step was the interesting one. So now we've got this x refers to a heap cell that now contains the values 42 and 35. And that represents the value approximation that the abstracting abstract machines sort of imposed on us. But also, we've got this heap cell containing continuation frames. You cannot see my mouse pointer. And it has 2 frames. So that means that when we return to the continuation contained in that cell, we actually need to consider both alternatives. And that means that we're actually going to go back in time. We are going to return to a continuation that we had already returned to. So whereas where the 42 and the 35 represent approximation of the value space, this having 2 continuation frames in the same heap cell is approximation in the control space. OK. And so we end up exploring some infeasible paths, paths that would never arise, that don't arise in the real program, and then the result is imprecise too. According to our analysis, this program could result in 42 or 35. Okay, but we have a continuation. It's store allocated, but we still have access to it. So we can apply garbage collection to it, just like we can with a regular interpreter. And so if we do that, the story changes. So same setup, but we're going to garbage collect every step. And this does two things. One, it removes the value imprecision that we saw earlier. And it also removes the control imprecision that we saw earlier. Because the old continuation frame that we had already returned to is collected before we attempt to return to it again. Now, garbage collection. So the point here is that garbage collection has actually changed the meaning of our abstract interpreter. It has made it more precise. So garbage collection in the setting of abstract interpretation is semantically relevant. But I want to talk more about this control imprecision. In this example, garbage collection was able to remove any imprecision in control, but that's not true in general. In general, there are programs and control flow that garbage collection can't help. So just to finish this off, by the end, with garbage collection, we have this perfectly precise answer. Okay. But there are techniques that do allow you to only approximate in the value space and not approximate at all in the control space. And I call those stack precise CFA. Those are more commonly known as pushdown CFA because they use a pushdown model or a pushdown system to model the control flow. So let's talk about a relatively recent technique to implement those. Before I actually talk about that technique, what's happening morally with pushdown control flow is we are giving up control of the continuation to the analyzer. So our states will now not have a continuation, but they'll have every other component. And the analyzer is going to manage the continuation. But I want to talk about a relatively recent way of writing these pushdown analyzers called abstracting definitional interpreters. And this is really appealing because they look very similar to just a regular interpreter you would write. So you have this eval function that takes an expression, an environment, and a store, and you match on the expression. And if you have like a let expression, say, then you'll evaluate. You cannot see my mouse. You'll evaluate the let bound expression, and then you'll get the results, and you'll evaluate the body. I'm using this monadic bind to suggest that there's something really interesting going on with the results. It's not just simply, it's not the bind of the meta language, you have to do something else. But it's a really great way to, and like straightforward way to write abstract interpreters. So let's see kind of what happens. I'm going to just run through this real quick. So this is with full, without loss of precision in the control space when we execute this program. So in a pushdown setting, we don't have access to the continuation. And so I just don't even render it. And so we evaluate this. And here's where we end up with 42 and 35, so still an approximate answer. And also we have these things in the store. And some of them might be garbage, some of them might not. But we don't know because we need the root set of reachability, and that is contained in the continuation. No, we weren't even done. Okay. Okay, so now I'm going to totally, I'm going to give you the punchline. No, one of the punchlines, which is this is a solved problem. And the solution is to have the abstract interpreter give you the root set, or an operator to get the root set as a primitive. So this has been done. And so you can write this, you could write a garbage collector for your definitional interpreter where as long as your abstract interpreter gives you this root set. But this is unsatisfying because it means that the evaluation of an expression, so earlier I illustrated that garbage collection is semantically relevant to abstract interpretation. But if we depend on the root set, that means that in some sense, the evaluation of an expression depends on its continuation. And that is unsatisfying. Because in the absence of like control operators and control effects, it shouldn't be like that. So this work is a way to overcome that limitation. And the insight comes from this, the fact that in this interpreter, the store of the expression, of the outer let expression, is in scope after you've evaluated the binding or the bound expression. And so with that insight, the key idea is why not have the store, instead of closing the entire program or the whole stack, have it simply close a single environment, the environment of the expression it accompanies. So if we were to do that, we could perform garbage collection without this primitive. All we would need was the root set from the current environment. So let's look at what this looks like. So we start with this program. We have this single store, this empty store. And when we get this sub-expression to evaluate, it has its own store. And then it returns, and its result is put in the store of the continuation frame, the top continuation frame, and we continue. And so here we are. We have this call to ID 42, and ID points to its own copy, sort of the identity function. And when we call it, that identity function is no longer reachable with respect to that expression, so we garbage collect it. And then we return. And here, 42 is not reachable, so we can garbage collect it, and so on. Okay, so without any access to the continuation, we've been able to perform garbage collection. So the store, which models the heap, is not only a repository for allocation, but it's a way to communicate effects, mutative effects through evaluation. And if we are decomposing the heap in this way, how do we communicate effects? So the solution we have is to let every evaluation result in both a value and an effect log. And when you get the results of an evaluation, of a sub-evaluation, replay the effect log on your store. And that turns out to work. And I know I've made this seem like an afterthought here, but it's actually a big critical component in the paper, if you want to read it. Okay, and I also talk about some other things in the paper, like why am I doing this if this is a solved problem? And sort of the short answer is, when we have control flow analysis that doesn't introduce imprecision in the control space and doesn't depend on the continuation, evaluation doesn't depend on the continuation, then we're in a good position to start exploring compositional CFA, where we can, so we'll actually explore less of the execution space, and that will make things like memoization much more profitable. But there's more discussion in the paper. I didn't talk really much about timestamps, but what we've done here is, instead of threading the store through execution, we treat it compositionally. And if we do the same thing with timestamps, instead of threading them through execution, treat them compositionally, we go from a KCFA abstraction to an MCFA abstraction. That is, instead of using the last K call sites, our abstraction is now the top M stack frames. And there are some reasons and some evidence that is a superior abstraction. And then these two things together, they kind of just lead toward compositional CFA, where the control flow analysis of an expression truly is a function of the analysis of its subexpressions. And I find that highly appealing. So thank you for your time.
We have plenty of time for questions.
So in some formulations of a if you add abstract garbage collection, I think if you have a global store, things become more difficult to determine that they're actually unreachable, right? But if you split them up into, like, say, a flow-sensitive analysis where you have a store for each syntactic expression, then you can say that something's reachable here or unreachable at the current expression, but was reachable before. And your presentation kind of nicely simplifies things in a way that makes it more intuitive, but it left me wondering if there was any issues around that in the way that you're doing things.
I haven't encountered any issues with that. I think that's an interesting idea. So you're saying, like, right now I'm sort of like, my granularity is finer than it might need to be if I were to, like, ignore, like, the environment and just consider the stores common to a given expression. Is that kind of what you're saying?
Well, I guess it depends on how you construct the analysis. But if you have a set of states for the current, if you have one global store for a set of reachable of states, you can't really tell unless you have a separate frontier or something like that which states are actually relevant at this point. And so you sort of, anything that was ever found, once you get to an analysis, you're still keeping around all those old states, right? And so those old states still map to things which are garbage now, but weren't garbage when those states were first encountered. And so if you have a frontier, or if you do a flow-sensitive analysis, there's various different techniques that enables abstract garbage collection to be effective again, right? And so I'm just wondering how that factors into what you've done.
I don't know entirely, but I'd like to talk more about it.
Yeah.
Any other questions?
I mean, are you? So you sort of said that there's a way of going and accessing the root set for the stack, but I'm wondering if you were a little unclear if you exactly how you represented the continuations. And I was kind of wondering because there's a difference in ADI. They have a continuation store, which is part of, like, a memo table, right? And then they key that memo table in a certain way, which gives you perfect stack precision. And in the PDCFA model, you have this, stack deltas annotated on edges between states. So from one state to another, if you push something onto the stack or pop something into the stack, then you annotate that on the edge. And then you have an epsilon closure graph, and then you can go compute, what are my top stack frames and work backwards. But those seem like two slightly different ways of going and collecting the root set. And if you use the way that ADI does it, I would think that you could just use the standard algorithm for going and traversing the heap, because you still are putting all the continuations in the heap effectively. Whereas you kind of need a different. I see how it's possible in either way, but the way you described it sounded to me more like PDCFA. But that said this was sort of a special operation, whereas it wouldn't need to be necessarily if you did it the way that ADI does it. If I understand how ADI does it correctly.
I think this technique is oblivious to the way you get pushdown precision.
Right. Okay.
So it's just it exploits only the fact that the store of the caller is accessible once you have your results. Once the callee's results are obtained.
Okay.
And so you have a store essentially for every stack frame. And then you just say, well, instead of having that be a global store, just let that close the stack frame.
Okay. And then that's also my answer to my question about the flow sensitivity also, because I think if you have a different store for each stack frame, that it makes sense that you'd be able to determine the latest stack frame something is garbage, whereas in a previous stack frame it wasn't.
Right. Yeah.
Any questions from everyone else? All right, thank you.